So hi, welcome back to our radiation heat transfer learning journal. The last video we were talking about how to do proper substitution of this tau prime term because we are talking about measuring the distance from the top. Okay, so before I start that, I realized that after looking through some of the equations and formulas, there was something a little fishy with my formula, especially with the limits over here. So probably if you're pretty sharp, you would have noticed it in the past few videos already. But now I'm here to rectify that problem. So as you see, we are varying this d tau prime. Even in the positive case, we are varying this d tau prime from the bottom. So where is tau prime? Tau s prime is here, but tau prime is here. The corresponding value of tau prime is over here. So we are varying d tau prime. So we are integrating from tau prime equals to 0 to tau prime equals to tau L or tau. So there should not be a modification by this mu over here. So that tau should be the correct value there. So everything we have kind of derived in the last few videos was slightly wrong because the limits of the integration were wrong. So that will need to be corrected. So wherever I see this tau prime over mu or tau over mu, I will need to change it. And this is what I'm just going to do now. So everywhere we see this tau, whether it's tau over cosine theta or anything like that, we'll need to replace it. Because again, we are replacing all this. So yes, if it's d tau s, then yes, it will be tau over cosine theta. I suppose that we are doing the changes in. But if we change the variable here to d tau s, then this will have to be changed back to tau, because this d tau prime is what we are varying rather than d tau s prime. So other than that, we are good, and we will need to go back to our equation at the bottom to see where we are headed next. Okay, so yeah, I think like I was saying before, a blind substitution will not work. So this should be tau also before we change anything. And probably the best way is not exactly to change the substitution for this, though yeah, what this physically means, of course, over here, it is the exponential of the length. Okay, where is it? It is this length minus wherever. Okay, as we were discussing before, it is the whole length, right? The whole length, this whole length, which is this quantity here, which I'm highlighting, right? This whole length, this whole blue line I'm drawing here, minus this length, which I'm highlighting here, which is the second term here. Okay, so that substitution has grounds in it. Okay, but you would have noticed that the tau L's actually cancel out anyhow. So it is pretty convenient for us. We'll just write it as such. And let me highlight this in red to say we haven't figured the limits out yet. So this will be highlighted in red. But as far as we are concerned, the tau L's actually cancel out because there's a minus tau L here and a minus tau L here. So the tau L's actually cancel out. We have a common denominator of mu. And now all that we are changing is this d tau prime. So where does the tau prime start, right? So if you're looking at the tau s prime or d tau s prime, it starts from here, right? It starts from here and goes all the way up. So tau prime will start here and will go all the way up here. So these are the two limits. So yeah. So remember the physical meaning of this. We start with this whole length and we subtract whatever length we have here as determined by this d tau prime, right? So integrating, we will need to figure out what is the start point and end point of tau prime. So the start point of tau prime is here at tau L, right? Not tau L over cosine theta. So we are going with the physical interpretation of it rather than, blindly substituting tau prime over mu into tau prime minus tau L over mu. So this we know what we want to do conceptually, but this is not the correct mathematical way to do it. So I'm just going to cancel that. So make note for future references. Always try to go with the physical, physical representation, the physical meaning of a system if at all available. So okay. So anyway, regardless how we go, we need to start from tau prime equals to tau L. So tau prime equals to tau L, and then we end at tau. We still end at tau, which is not an issue, but the limits of the integration have changed. So this is something very important to take note of. And if we were to look at this textbook derivation, we will see, okay, for the I2 tau theta, it will be this. Let's copy this over. Okay, copy is not allowed for this title. Okay, fair enough. Let's use snipping tool. And let's check what is being used here. So we have I2, or rather this I omega, which is representative of the intensity at the top plate. So where's the top plate? Top plate is here. Okay. Intensity at the top plate. Okay. Yeah. So I2 or I omega in this case is referring to the radiation coming from the top, and the second term, of course, is the integral of all the source term, and you kind of do this exponential decay by this optical thickness, which is tau minus tau prime over mu, or tau over mu minus tau prime over mu, which is the same as exponential tau prime minus tau prime divided by cosine theta. And of course on the right here, the last little bit here is d tau prime over mu, which is d tau prime over cosine theta. If we use the substitution, mu equals to cosine theta. Of course, you can do a simple sign change if you want to have if you want to have tau at the bottom and tau L on the top. Otherwise, it's more or less the same thing. So yeah, if we take a look over here, we'll see the converted final form of the equation. From mu equals to 0 to mu equals to 1, we will have this form for I plus. From mu equals to minus 1 to mu equals to 0, we'll have this form for I minus. So we can do what we need to do. We can actually just continue our derivation for why we are doing this intensity, the form of these intensities in the first place. It is for this very purpose of finding this Q, right? You need to find this heat flux, not just any heat flux, it's the scalar form of the heat flux. So back to our scalar heat flux, right? Scalar heat flux. This is our scalar heat flux, and what we need to do is to integrate this I, right? This I minus and I plus, right? I minus and I plus from mu equals to minus 1 to mu equals to 1. So this one actually, the I minus is from mu equals to minus 1 to mu equals to 0. Why? As we have stated before, if we take a look at this, here, from mu equals to minus 1, which is okay, mu equals to minus 1, that is over here, I believe. Okay, so let's take a look. Yeah, so where is mu equals to minus 1? Let's take a look at our diagram again. Yes, so mu equals to minus 1 is when we have a full theta equals to 180 degrees. So, okay, so when we have a theta more than 90, that's theta equals to pi by 2 or more, we will have the thing actually go negative. So that means it's coming from the top plate. So mu equals to minus 1 is where theta equals to 180. Okay, let me use a different shade. This light blue shade will do. Mu equals to minus 1. This one is getting really crowded. Let me use this. 2 plates again. Okay, we use this. Normal vector going up. 1, 2. Alright, so mu equals to minus 1 will be something like this because the vectors are going in the opposite direction. Theta equals to pi. Right, so cosine theta equals to mu equals to minus 1. So if they are going in the same direction, for example, for example like so, okay, one like that, and of course use a blue color. The arrow goes like this. This is theta equals to 0, cosine theta equals to mu equals to 1, right? So for mu equals to 0 to 1, the relevant intensity is I plus, right? The intensity will be I plus because that's the intensity going upwards. For mu equals to minus 1, for mu between minus 1 and 0, we look at I minus because this is 90 degrees, right? So mu equals to 90 to mu equals to 180, mu equals to 0 to mu equals to minus 1, then we look at the intensity coming from the top. So intensity coming from the top is obviously from the top plate. That's what I meant. Yeah, so intensity coming from the top, that is what we are looking at. If mu equals to minus 1 to 0, and for this we have mu equals to 0, 0, 2, okay, let me try again, 0, mu, and 1. Okay, so this is what the radiation equation looks like. So what we have here is we can split this integral into 2 parts, right? Split this integral into 2 parts. So let's just okay, copy and paste this. So remember, from mu equals to 0 to 1. Okay, let me copy and paste this first. 1 and 2 here. Let me bracket this up so I don't forget the 2 pi factor. So the first one is of course mu equals to 0 to mu equals to 1. And the second one is from mu equals minus 1 to mu equals 0. And that will have our radiative heat flux, the scalar heat flux. And just for clarity, we'll have I plus over here. And we will have I minus over here. Right? So once we have that, let's substitute our relevant expressions. So we will have I plus, so it will come from the bottom, intensity of the bottom plate because it's going upwards. And this one will be intensity of the top plate. So I'll just write bottom and top for a lot of clarity. So there's no mix-up, no mishap, and you know what I'm talking about. So I plus at the bottom will be this, and I minus, so it'll start from the top, it will be this. And this is more or less our expression of what we need to do. Okay. So if we just do this simple multiplication in, we will get the mu over here and the mu over here. So likewise I can do the same for this. Yeah. And we'll more or less get the appropriate expressions that we need. So yeah, what we'll see here is what exactly what the textbook is giving us. Alright, so I'll just copy and paste this expression. So the expression is, of course, you have this 2 pi, then you have I1 and I2, right? I1 being the one from 0 to 1. So this is the bottom intensity. So it depends on mu, right? Depends on mu. It can depend on you, or you can kind of make it uniform throughout. Yeah, you can make it uniform throughout. And you can have a I2, which is the intensity from the top. So this is this term over here, actually. The same in physical meaning. And the other thing is that you have to integrate the source terms. So you see this source term is, I believe this is from 0 to tau, so this is the source term we are talking about. So we kind of like multiplied the mu's in, so the mu's kind of cancel. And then we just have the tau prime left. So I can just do this effectively. I can get rid of the mu's, one less headache. Alright. And likewise, for the other term, we will have from tau L to tau, or we can just reverse and we get a negative sign over here. And that will be it. That will be it. However, of course, you do see a very interesting thing here. If we just reverse the signs, as you see over here, we can actually get 0 to 1, right? Because it's a mirror reflection when we do this d mu. Remember the cosine has a mirror reflection over here, where this cosine theta equals to cosine theta pi minus theta. So you can basically use that. I won't show you the derivation, but you can use that to change the limits from 0 minus 1 to 0 into 0 to 1, and then we'll just get this negative sign outside. It's a little bit of math magic there. It goes from I and I2, rather than depending on mu, you can just replace mu with minus mu here. You get this trick here. It will be okay, so that you can have the same kind of limits, and you can kind of combine its integrals, but this is perhaps the final expression for QR prime. If you take a look at the textbook, we don't have any more definitive way of showing what Q tau actually looks like. It is left in an implicit form. So without further simplification, even the analytical solution is left in implicit form, unless the case is really so simple that you don't need to bother with all the funny integrations. You have to leave it in implicit form. Okay, so the other thing we want to find out, besides the heat flux, it is basically the, what do you call that? What was I looking for? I think divergence. Yes, divergence of heat flux. Yes, so this is the divergence of heat flux I was talking about here, right? And remember, I think we derived in the other videos, after doing this, where did I put that? Oh, maybe I have not quite derived it yet. Okay, now we want to find divergence of heat flux. Okay, so what was the basic form of this? Before we talk about 1D cases, there was a very much what do you call it? There was a simple form, and this is the form we are looking for. Yes. Okay, so let's scroll to the bottom. Let's just paste this formula there, and then we can see what it looks like for the 1D case. So, all right, so that's it. The 1D case, we will have kappa lambda inside. We will have IB lambda. This does not really need any kind of new derivations whatsoever. Okay, so this is for a particular control volume in that one such location. The only thing we need to consider is G lambda, or rather just G, the spectrum integrated form. Okay, and what is G? It is basically all that you see here, and we can discuss how to derive this in the next what do you call that, video, in the next video. So thanks for watching. I'll see you guys again next time. Bye bye.